Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Welcome back to our Deep Learning course. Today, we're starting Chapter 4, Basics of Convolutional Neural Networks 1. I'm still your lecturer, Chi Jiaming. Convolutional neural networks, CNNs, are super important for image tasks. Let's explore their basics step by step. First, let's clarify the learning objectives of this chapter. By the end, you'll master 3 key points. First, the basic structure of a convolutional neural network. Second, the concept, classification, principle, TensorFlow implementation, and related properties of convolution. Third, the concept, classification, principle, and TensorFlow implementation of pooling. Let's keep these goals in mind as we learn. Part 4. 1. The basic structure of convolutional neural networks. First, what is a convolutional neural network, CNN? It's also called a convolutional network, and it's a type of neural network widely used in image processing and computer vision, like recognizing objects in photos or analyzing videos. Its fundamental structure has 5 core layers, each with a clear role. Input layer takes in the original image data, like pixel matrices. Convolutional layer extracts more abstract features from the image, for example, from simple edges to complex shapes like eyes or ears. Pooling layer reduces the number of parameters in the network, makes the model smaller and faster, without losing key features. Fully connected layer prepares for the final classification task, connects all previous features to make a prediction. Output layer outputs the final result, for example, this image is a cat, or this is a dog. Let's look at the structure diagram on the slide. It shows the typical flow of a CNN. Start with the input layer, then go through convolutional layer 1, does convolution, pooling layer 1, does pooling, convolutional, layer 2, another round of convolution for more features, pooling layer 2, another round of pooling, then pass to fully connected layers, prep, for classification. Finally, the output layer gives the result. This layered flow helps the network gradually learn more complex features from the image, simple features first, then complex ones. Part 4.2a Popular understanding of convolution and pooling. Convolution sounds abstract, but let's use a simple example from the slide. Determine if a photo, like an ID card, has a bear, shown da. Think of the convolution process as a mechanized check. First, we have a convolution kernel. This is like a small photo that records the key features of Xiongda, like his round face or big ears. We use this convolution kernel to scan the ID card bit by bit, moving it across the ID card to check every position. At each position, we calculate the similarity between the convolution kernel, Xiongda's features, and the image part at that position. This similarity calculation is exactly what convolution is. The slide shows an example. When the kernel matches Xiongda's face on the ID card, the similarity score is high, like 0.99. When it doesn't match, the score is low, like 0.02. Now, let's talk about pooling, still using the check for Xiongda on ID card example. Do we need to care about every similarity score from convolution? No, to judge if Xiongda is on the ID card, we only need the maximum similarity score from all positions. For example, if one small part of the ID card has a 0.99 similarity to Xiongda's kernel, that's enough to say Xiongda's portrait is on the ID card. We don't need to look at other low scores. This taking the maximum value operation is a common type of pooling called max pooling. To sum up, convolution calculates local similarity between the kernel and the image. Pooling selects the most prominent similarity, like the maximum, to simplify the result, keeping key features while making the data smaller.